an exact and precise way, instead of approximating the instantaneous rate of change, is to use the limit definition of a derivative, the limit as h approaches 0, of f at x plus h minus f at x all over h. You can use this in order to calculate any slope of the tangent or any instantaneous rate of change. Let's use it for this example. Find the instantaneous rate of change of f at x is equal to x squared at x is equal to 2. So we need to have what f at x plus h and f at x is. It's easy to know what f at x is. F at x is given to us. F at x is equal to x squared. Then we're going to need to use f at x plus h. So f at x plus h is, what does it mean to find f at x plus h? It means take x plus h and sub it in for x into the function. We can expand and simplify here to get x squared plus 2xh plus h squared. Keep in mind, to square a binomial, you square the first, you double the product, and then you square the last. So let's take f at x plus h and f at x and write it into this formula. So IROC is going to be equal to the limit as h approaches 0 of f at x plus h minus f at x all over h. We can sub that in. So the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. For limits, the first check is to always use direct substitution. But every time for the limit definition of a derivative, if you put 0 in here, you get f at x minus f at x. That's 0 over 0. So it's an indeterminate form. We're going to have to use some other way to evaluate the limit. What's the goal, though? The goal always is to cancel out an h. That's the piece in the denominator in the numerator that's giving you the indeterminate form, 0 over 0. So let's do some work to cancel out h. You'll notice there's an x squared here and a minus x squared here. So those two cancel out. Now we'll be able to factor out an h from this expression. You'll be left with 2x plus h all over h. Now we can cancel out the h's to be left with the limit as h approaches 0 of 2x plus h. We can sub in now. But we're subbing in for h because it says h approaches 0. In the limits that we did before, be careful because it was as x approaches a or some number. So we're going to sub in 0 for h. We get 2x. This is the slope of every tangent. This gives us the slope of every tangent on the function f at x is equal to x squared. To find the one that we needed it as at x is equal to 2, so you simply sub in 2. And you get 4. That's the instantaneous rate of change of f at x is equal to x squared at x is equal to 2. It's an accurate way to do it without approximating.